This is the Core 4 differential equations test that you have recently completed, and I'm going to go through the 3 questions one at a time. Now, as usual with these, the best way, most you're going to get out of them is when you actually stop the videos and try and complete the questions from when you understand. So as soon as you think you understand, stop the video, try and complete it from that point, and then you can restart the video and see if you're correct. Okay, so don't just watch it, try and work through it with me at the same time. So here's the first question. We've got to solve this differential equation, and the differential equation is dy by dx is equal to x to the power 4 minus 1 divided by x squared y squared, given that y equals 2 when x equals 1. So these are the boundary conditions for our differential equation. So we're looking for the original function of y in terms of x. Now the first thing we have to do on this particular problem is split the variables, so that when we integrate with respect to x, we're left with an integral with respect to y on the one side and an integral with respect to x on the other side. So hopefully that will become clear in a couple of steps time. So we're going to multiply both sides by y squared first. Okay, so we split the variables, and now we're going to integrate each side with respect to x. So we haven't broken the basic rules of the equation. We have done the same thing to both sides. We've integrated with respect to x. Now this is a step that is often missed out, and I'm quite happy for you to miss it out as long as you understand what's going on, because of the left hand side now simplifies to the integral of y squared with respect to y, and we've got to integrate the right hand side with respect to x. What you're integrating with respect to is very important, so it's very important that you don't forget to write it in. Okay, so it's one of those things that you were reminded of when you started integration. Before we start integrating the right hand side, we should see if it simplifies, rather than trying to overcomplicate the work we're doing. Now we can divide both of our every term in our fraction by the factor x squared, and we will get x squared minus 1 over x squared over 1. So effectively we're cancelling we're cancelling this factor of x squared. Now there is no x squareds in the number 1, so we're left with a fraction. But what that then simplifies to is x squared minus x to the minus 2 dx. Now I've recorded a video for GCSE students on simplifying algebraic fractions, and if this is a step that you found difficult, it's well worth going to watch that video, I think, on the same website, but it's under the how to do algebra section. So I recommend you go and have a watch of that if you found that step difficult. Don't be too proud to watch it. So now we're going to integrate. We're going to integrate this with respect to x and this with respect to y. So the left hand side integrates to become a third of y cubed, and the right hand side becomes a third of x cubed plus x to the minus 1 plus a constant k. And now we can multiply through by every term by 3, and we get y cubed equals x cubed plus 3 over x, because that's the same as x to the minus 1, plus 3 lots of a constant or a constant. Now that is the general solution to that differential equation. That's the general solution. But it's possible for us now to work out the particular solution, or the specific solution for this particular boundary case, by substituting our initial conditions. Y equals 2 when x equals 1, and we get 8 equals 1 plus 3 plus c, so c equals 4. So our solution is y cubed equals x cubed plus 3 over x plus 4. Now we could have cube rooted both sides, but that's also a good enough answer. So now we're going to look at question 2, and this is a harder problem, because it's wordier, and I know that you're not as fond as wordier questions because there's a level of interpretation which you have to get right. So we've got an anthropologist is modelling the population of an island A. In the model, the population at the start of the year is P, and the birth rate is 10 births per 1,000 in the population, and the death rate is M deaths per 1,000 in the population per year. And we've got to show that that differential equation is true. Now, it's only worth 1 mark in the exam, so it's an important mark to try and get, but at least if we didn't get it right, we can still carry on and work on section B, C and D and so on. Okay, if it was one of those questions where you have to derive the differential equation before you can do the rest of the program question, then it's a bigger problem if you can't derive them or set them up. So please work on that if that's something you find difficult. Now what we've got is we've got the population P, but we've got the rate of change of the population. Well, if you think about a population changing, and in this case we're only considering two factors, the births and the deaths. There's 10 births per 1,000 of the population, so there's 10 times by P over 1,000, and that's how the rate of change of the population would increase if there was just births on the island. But there's also deaths, so you've also got to subtract from that M lots of the population divided by 1,000, so per 1,000 of the population. Okay, and if you now factor that, you get 10 minus MP over 1,000, as you were asked to do. Now often if you look at what you were asked to show and what you were given with, you can just using logic get there, but just try and think about the actual particular problem. In this problem we've got a population which is varying, and the rate of which that population changes is dependent on the numbers of the births and the deaths. The births add to the population, the deaths subtract from the population. So that's a different differential equation. Now at the start of the year, the population was 108,000. So we've got the boundary conditions that when t equals 0, p equals 108,000. So basically what we're doing is we're solving that differential equation, and this is where a number of mistakes can crop in. So here's the differential equation. M is a constant, but p isn't. So if you integrate both sides with respect to t here, you are trying to integrate the right hand side with respect to t, and you'd end up trying to integrate p with respect to t, and that's not something you can do. So what we've got to do is we've got to try and split the variables so that we integrate both sides with respect to time. We're left with an integral with respect to p on the left hand side and then integral with respect to time on the right hand side. Now it's up to you how much of this you use on the split. Now I would always just take the 1 over p, just take the p to the left hand side, divide both sides by p. Now I haven't put the intermediate step in this time, but if you want to see how I got there, then just look at the previous example. It doesn't matter if I'd taken 10 minus m over 1,000 to the left hand side, it will work exactly the same way. You just got to be careful you integrate. And this is an harder thing to integrate than this side. So why it's harder to integrate is because you've got a 1 over p, and this is just a constant. So now we're going to integrate. Well, we integrate the left hand side with respect to p, and we get the log of p, natural log of p, and you integrate the right hand side with respect to time, and you get 10 minus m over 1,000 times by time plus a constant. And that's my point about the right hand side being easy to integrate, because it's all a constant. It's just like one single constant there, so all we have to do is just integrate that as a whole, and you get that times by t. Now we're trying to get p equals something, so that's log of p, e to the log of p would equal e to the 10 minus m over 1,000 t plus k, and you might want to write that in a square bracket so you realise it's the whole of that. Now remember, log the base log of p, e to the log of p is p. And in this case the population is going to be positive, so I'm not going to include the modulus. Okay. Now, we haven't applied our boundary conditions yet, and we can apply our boundary conditions in this form, but remembering our laws of indices, we can also write this as e to the k lots of e to the 10 minus m over 1,000 times by t. So the population equals e to the k lots of e to the 10 minus m over 1,000 times by t. And e to the k is a constant, so we can write it as p equals e to the 10 minus m over 1,000 times by t. So that is now the general solution, which we can work on with the boundary conditions, initial conditions, to find the particular solution that we're looking at in this case. And that is when t equals 0, p equals 108,000. So 108,000 is equal to a multiplied by 1, because e to the nothing is 1. So our particular solution in this case is p is 108,000 lots of e to the 10 minus m over 1,000 t. And that would give you the full 4 marks. So that's the one we're going to be using in the remaining part of the problem. Now if we look at it, what that's saying is the population starts off at 108,000 and will be rising exponentially. So now we're going to look at part C. And it says the population doubles, so the population is going to become 216,000 after 100 years. And we've got to find the death rate that would allow that to happen. So we substitute those values carefully into our formula that we derived. And what we're going to do then is solve that equation for m. So, as I said at the beginning, you get the most out of this if you do it yourself. So at this point you could pause the video, see if you get it right, and then start it again. But working through it, we're going to first of all divide both sides by 108,000, and we'll get 2 equals e. Now we're going to divide the top there. 100 divided by 1,000 is a tenth of 10 minus m. So we just simplified it slightly. Now we're going to take the natural log of both sides. And then we're going to rearrange, so that's 10 log of 2 equals 10 minus m. So the death rate will be 10 minus 10 log of 2, or 10 lots of 1 minus log of 2. So that's the death rate. And you can work that out, but that's the exact answer. Okay, so work it out by putting it in your calculator. But that is the exact answer. So that's part C. So the last part now is part E, and it's asked us to explain why the population cannot be double in less than 69 years. So the way I'd like to look at it, and there are other ways of doing it, but to say, well, the rate of change of the population is built up by this relationship between the birth rate and the death rate and the population. And when we solve that differential equation and we use our particular boundary conditions, then we get that formula for the population as a function of time. Now, to maximize the rate of change of the population, we want to minimize the death rate and maximize the birth rate. But we can't change the birth rate in this case, it's fixed at 10 per 1,000 of the population. But we can minimize the death rate by setting it to be 0. Now mathematically we can set it to be 0, but any biologists studying this may want to argue with that. But mathematically we can say m equals 0. And then that means that we can get population equals 108,000 e to the 10 over 1,000 t, or 108,000 e to the 100th of t. Now if we look at how long it takes now to double the population C, if that's less than 69 years, so 216,000 equals 108,000 e to the 10 over 1,000, or 1 over 100 t, we get 2 equals that, and we can take the natural log of both sides and times by 100, and we'll get 69.3. So it's not possible to double with less than 69 years. Okay. So question 3 now. It's a difficult question because there's a lot of trigonometry in it, so a lot of students don't like this question because they understand that they've got to solve a differential equation, but the trigonometry hurts them. So let's look at it and work through it slowly. Again, as soon as you think you know how to finish it, pause the video and finish it for yourself. So we've got the differential equation, sec squared y over cos squared 2x dy by dx is equal to 2. Now on this problem, like the last two problems, we have to split the variable first. So I'm going to write that as sec squared y dy by dx is equal to 2 cos squared 2x. Now I'm going to differentiate both sides with respect to x. Now one of the things that's a bit confusing on the left hand side is I said I was going to integrate both sides with respect to x, but there it is, integrating with respect to y. But look at the first example for that, and you'll see the intermediate step and why we end up with an integral with respect to y. Right, now we can integrate the left hand side first of all. It's a nasty looking integral, but you should always remember that you've got a list of integrals that you're given at the beginning of the exam on the green booklet, and this is one of those integrals, and it becomes tan y. So that's the first part, and then now we've left with the second part, and now this is where you need to know your trig identities. So 2 cos squared a is equal to something. Now try and write down what 2 cos squared a is equal to without looking in your book. So cos squared a is equal to cos 2a plus 1. So you really need to know this stuff as quickly as possible. And you're running out of time because your exam's in January, remember. So we've got 2 cos squared a equals cos 2a plus 1. So if we just thought about that and we thought, well hang on, what if we had 2 cos squared 2a in there? Well, that's 2 lots of a. So we're going to have 2 lots of a here, or cos of 4a plus 1. So you can modify the trig identities we have by substituting valid alternatives. So we could have also written this as 2 cos squared. Now this wouldn't have been valid or useful for this particular problem, but it might be useful in another problem. So look out for that. Okay, so the point is, in the right hand side it's double the whatever the angle is on the left hand side. So that means instead of writing the integral of 2 cos squared 2x, we've got the integral of cos 4x plus 1 with respect to x. And that is something you can integrate. That integrates to, just get that side boxed up, 1/4 of sine 4x plus x plus a constant. So after we've integrated both sides, we get tan y equals 1/4 of sine 4x plus x plus a constant. And that's the general solution. That's how we can leave it. General solution. In part 2, we're asked for the particular solution in which y equals 1/4 pi when x equals 0. So now we can substitute in our boundary conditions of y equals 1/4 of pi when x equals 0, and we get tan of pi by 4 equals a quarter of sine of 0 plus 0 plus k. Now don't forget you need your calculator in radians. If it's on degrees, then make sure it's in radians. And we get k is equal to 1. So our particular solution is going to be tan of y equals a quarter sine of 4x plus x plus 1. There's sometimes a temptation to stop there, but we should always look to make sure we finish the question. And the last part of the question was find the value of y when x equals pi by 6. So again, we can substitute that in, and we get tan of y equals a quarter of sine of 4 lots of pi by 6 plus pi by 6 plus 1. So y equals tan to the minus 1 of a quarter of sine of 4 pi by 6 plus pi by 6 plus 1. And if you put that into your calculator, you should get the correct answer. And I get y to be 1.049, or y equals 1.05 to 3 significant figures.